Hi, my name is Thomas and I'm going to present our paper on learning keypoints from synthetic data for robotic cloth folding. Robotic cloth folding is a challenging problem due to its deformability, which results in infinite degrees of freedom. Nonetheless, complete pipelines for cloth folding have been created by leveraging the observation that it suffices to know the position of a few semantic keypoints or landmarks. These pipelines, although very impressive and robust, have limited potential to generalize to diverse environments, as they rely, for example, on segmentation techniques that assume a known background color distribution. In this work, we attempt to overcome these limitations by leveraging the generalization capabilities of neural networks. We train a neural network to detect towel corners and transfer this network to a real setup, which allows us to fold towels with a simple open-loop trajectory. By using procedural data generation, we can train this network without having to collect large data sets. We can also easily generate all desired variations in the dataset. Our pipeline contains three components: the procedural data generation, the keypoint detector, and the scripted fold trajectory. I will briefly introduce them in the next slides. To generate the training data for the keypoint detector, we create a 3D scene in Blender. We randomize the geometry and pose of the towel, as well as its material. For the towel material, we create a simple noise texture, as creating high-fidelity textures of cloth is time-consuming. The camera position is also randomized to make the network generalize to different camera poses. The major issue when training neural networks on synthetic data is the sim-to-real gap, or the decreased performance when transferring the network to the real world. To overcome this, we use domain randomization. We sample objects from the Thingy10K dataset to provide negative distractors. To introduce diverse lighting, we add high dynamic range images as environment maps. Finally, we add a random material to the surface to introduce spatial patterns. For the keypoint detector, we use a UNet-inspired architecture with residual connections in the bottleneck to combine spatial resolution conserving paths with a downsampling path for a larger receptive field. The network outputs a single heat map that contains all detected corners of the towel. After training on the synthetic dataset, the network achieves an average precision of 82%. We then manually define the grasp pose and the circular fold trajectory in a local frame on the towel. Once the corner locations are known, we can transform this local frame to the frame of the robot and fold the towel. To evaluate the system, we gathered 20 towels and divided them in two groups. Within distribution towels that have uniform textures as modeled in the synthetic data, and out of distribution towels that have unmodeled textures. The robot attempts to fold each towel under various circumstances. We change the towel's initial state, the environment lighting, and the presence of random objects in the scene. We use the grasp success rate to measure the performance of the keypoint detector and evaluate the complete system with a fold success rate. The system has a grasp success rate of 80% on the in-distribution towels. Grasp failures are due to wrong or incomplete keypoint detections, indicating that there is still a sim-to-real gap. In future work, we aim to further explore this to provide more insights and a more principled approach to procedural data generation. The difference between grasp and fold success rates are caused by limitations of an open-loop unimanual fold trajectory. In most failure cases, the corners of the towel get bent, resulting in a failed fold. For some towels, the difference in material properties causes the fold to fail. To conclude, in this paper we showed how to use procedural data generation to train a neural network to detect towel corners and use them to fold towels with an open-loop trajectory. This shows that synthetic data generation can be used to solve perception tasks for robotic cloth manipulation. You can obtain more information in the paper or by visiting our poster stands.